Next, we have example 2-9, where we have this gate right here. You can see the hinge. This is the gate. It rests on top of the wall here. Has a weight sitting on it, and then a whole bunch of water behind it. And of course, if there's enough pressure, then this gate will be pushed open. That's why the weight is here. And so we're now asked to figure out how much weight we'd have to put here if this height is equal to 2 meters. And we're given the width of the gate, right, to get the forces, but we're told to neglect the weight of the gate itself. All right, so that's looks like a pretty standard static problem to me. So the first thing, of course, that we'll do is we'll do a free body diagram, right? So we can say this is the top of our gate, kind of goes down around the corner like this, and then we'll have a bunch of forces, right? So we can say we have our reaction forces over here. All right, we have our horizontal component, so we'll call that AH, and we have a vertical component, AV, and then we have our normal reaction down here because it's just sitting on there. Now we don't have a weight for the gate, but we have the weight that's sitting on there. That's all the way over here, so it'll be our W, and then of course we have all the resultant forces that are acting on our gate due to the water pressure. And so what we'll do is we'll break those down, right? We'll look at the one that is acting on the plate here, right? This only is going to have a vertical component, right? So we'll just give this a name. We'll say this is, call it F1, and then here, and we know that this is going to be constant, right? So that's why it's easy to do. Down here, we know on the horizontal or the vertical part of the gate, right? We know that the pressure will be changing because the depth is changing. So we'll add two components here, right? We'll say one that is kind of the rectangle that we can find, the other the triangle. So we'll say we have an F2 and an F3. Right, one for the triangle part, one for the rectangular part of that. And so I think the first thing that we'll do is we'll find out what all these different forces are, right? So if we think about F1, right, that's the one that's acting on the horizontal part of the plate. Of course, the pressure is going to be the same everywhere, right? So we can say we have, maybe we'll do the line in black. Right, so we have our horizontal line, and then we have a constant level of pressure acting on it. Make that one a little longer there, right? And we know what the value is of that pressure. That of course has to be gamma times 2 meters, right? Because it's 2 meters deep, because our H is equal to 2. So that'd be one of them. And well, let's just directly figure out what the force is have to be, right? So we'll have our resultant force is somewhere in the middle here. That'll be F1. So we can say F1 is equal to, well, we know the pressure is gamma times 2 meters. And we know that it's acting, the width here is 1.5 meters. And then we know that the gate in total is 0.6 meters. So that then, if we plug in our gamma, right, be 9,810 Newton per meter cubed, times, if we multiply all those together, we get 1.8 meters cubed. So we get our F1 is equal to 17,658 Newton. So that would be the forces acting on this part of the plate. Now in this direction, right, we kind of have a trapezoidal shape, and we're going to break that trapezoidal shape into two parts, right? So in total, if we think about it, it will look something like, let's go, our wall again is black, right? So we'll have our wall looking like this. Let this be our the vertical part of our wall, and we know that we have higher pressure here than there. So we'll have something that looks like this. Right, but we're going to break this apart. I'm going to say this is equal to a rectangular part. Oops, that was supposed to be blue. A rectangular part plus a triangular part. Right? That's what we get. Now, of course, we know that for our rectangular part, the height here is just going to be gamma times 2 meters, right? Because it's at the top of our plate right here, right? That's be this location, so depth is 2 meters. And for our triangle one, right, we know that it'll start at 0 and has a total depth of 0.75. So we can say this is going to be gamma times 0.75 meters. And based on that, we can then find what F2 is going to be and what F3 is going to be. So let's calculate those out. F2 is again as a rectangle, so that's always easy. F2 would be gamma times 2 meters. Now the wall has a length of 0.75 meters and an overall width of 0.6 meters. That would be 9,810 newtons per meter cubed times, multiply those together, we get 0.9 meters cubed, which makes sense because it's half of what the other one was. So we get 8,829 Newton for F2, and for F3, this is now a triangle, so you do 1/2 times the height is gamma times 0.75 meters. The length there is also 0.75 meters, and of course, overall width going into the page for us still 0.6 meters. And so that is then 9,810 Newton per meter cubed times 0.9. Oop, I have a typo up there. Fix that in a second. 0.9 meters cubed. Nope, I didn't have a typo. This was correct. F2, F3. I'm sorry. Let me erase that real quick here. So we have that looked in the wrong number. 0.3375 meters cubed. Slipped up to F2 for a second there. That's why I was confused. And if we multiply that in, we get 1,655.4375 Newton. All right, very good. So we have figured out what those are. So if we go back to our free body diagram up here, right? So that means the only unknowns that we're left with now are all the reaction forces and our weight, right? Because we're not given the weight. Now, if you look at this, you might get a little concerned, right? How many unknowns do we have? 1, 2, 3, 4, because we don't know what the weight is, right? How many equations can we get? Well, we can maximum get 3 equations out of our free body diagram here. So we have to think a little bit before we start acting. There's one more piece of information that we have to take into account, and that is that we're calculating all this for the point where the gate is just about to lift. Right? Remember from statics, we had the idea where things with friction were just about to move. Well, it's the same idea here. It's just about to lift off. If this gate is just about to lift, right? What does that mean for our force, our reaction force here at B, right? If I have something that's just about to lift off, there's not going to be any weight on it, right? There's no force. So we can say that we can figure out that B is equal to 0. Oops, write that down here. Maybe try to write it readable. Because gate is just about to lift. All right, good. So that now means we have 3 unknowns, and that is all and 3 equations. So now how do we solve this? Just as usual, right? We can do this in a smart way or in a long way, right? We could, of course, go in and do the horizontal sum of forces, right? That would give us our AH. And then we could do sum of forces and a moment around A, and that would give us AV and W. But we're not really interested in AH and AV. All we're interested is the weight that we have to place on top there, right? We actually ask for the mass, but we have to get the weight first. So what that means is maybe we'll just do a moment around point A, because then the only unknown is going to be W, and we can go from there, right? There's nothing other than W that's unknown, because we know B is equal to 0. And we already figured out what all these different F's are. So let's do that. Let's say that let's go back to blue. The sum of moments around not 0, around A is equal to 0. And what does that mean for us? Well, let's start with our big one. That's W. W is turning clockwise and at the distance of 1.5 meters. So it'd have to be negative. Minus W times 1.5 meters. Then B is 0, so we don't have to care. A, H, and AV both go through A, so we don't have to care about those. So the rest are our little forces here. So my F1 is going to go counterclockwise, so positive, and because it's a rectangle, we know that it's at the halfway point, so it'll be half of 0.15 meters. F of 1.5 meters, I'm sorry. So it'll be plus F1 times 1/2 times 1.5 meters. How about F2? F2 was from the other rectangle. It's turning also counterclockwise, and if this is also a rectangle, we know that's half of 0.75 then. So we have plus F2 times 1/2 times 0.75 meters, and then the last part is our F3, also turns counterclockwise. And because F3 is from a triangle, we know it's 2/3 from the top, 2/3 of 0.75. Right, so plus F3 times 2/3 times 0.75 meters. All right. The only unknown that we have is W, so we can go ahead and solve this for W, and we're done. All right, so maybe the first step we'll bring W times 1.5 meters to the other side, and we'll start in what we have left. So that means on a side here, this was negative, goes over, so all the other ones stay the same. So we get F1, half of 1.5 is 0.75 meters, plus F2, 1/2 of 0.75 is 0.375 meters, and then 2/3 of 0.75 is 0.5. F3 times 0.5 meters. All right, then we can divide everything by 1.5 meters. So that'd be F1, 0.75 divided by 1.5 would be 1/2. So we have 1/2 F1. And then if we divide 0.375 by 1.5, we get 1/4. And then 0.5 by 1.5 is just 1/3. F3, so good that we have a little more space here, so let's plug that in. That means W is equal to 1/2 times F1, 17,658. 658 newtons, plus 1/4 times F2, 8,829 Newton, plus 1/3 of the not quite so clean number. Fix that out there, 1,655.4375 Newton. All right, that all looks good. Can plug all that in, and that gives us 11,588.0625 Newton, or 11.6 kilonewton. All right, so we figured out that the weight that's pushing down has to be 11.6 kilonewton to prevent the gate from lifting if the height of the water is 2 meters. Right. So again, at that point, there's not going to be any force between at point B, because it's just about to lift off. All right, but we're not asked for the weight, we're asked for the mass. So we can convert that into a mass. Mass is equal to the weight divided by gravity. So it'll be 11,588.0625 Newton. Or let's write that as kilograms times meters over second squared. So we can see how that cancels out. Divided by 9.81 meters per second squared. That gives us a value of 1,181.25 kilogram. Let's make sure that we actually get the kilogram, right? We get the meter per second squared cancels out. And if we want to write that as a smaller number, we can say that as 1.81 megagrams, right? Because we're going one up. So we also call that tons, but it's difficult with tons because there's multiple different definitions of tons. So it's better to say megagrams. That makes it very clear what we're talking about. So to recap, if we wanted to keep this gate closed with a water height of 2 meters, then we'd have to add 1.18 megagrams of mass up on the corner here.